Welcome everyone. I am Carl Joseph Samuel from the Department of Biotechnology, Kamraj College of Engineering and Technology. Currently we are seeing the mass transfer operations lecture series. In this lecture we are going to see about the steady state diffusion in the fluids. So what is diffusion? Diffusion is the movement of molecules from a region of a higher concentration towards a region of a lower concentration till the equilibrium is obtained. So the molecules that are present in the higher concentration move towards the lower concentration region until the concentration of the molecules that is present is entirely equal in all the regions. So this process will continue until the concentration of the molecule is uniform throughout the system. So diffusion, it is a result of the random thermal movements of the molecules. So the diffusion process is governed by the Fick's first and second law, whereas the Fick's first law describes the flux of the species due to the concentration gradient, movement of the species due to the concentration gradient, and the Fick's second law describes the time dependence of the concentration changes. So there are two types of diffusion, one is molecular diffusion and another one is eddy diffusion. Molecular diffusion also known as the simple diffusion occurs because of the thermal energy of the molecules leading the generating the movement of the molecules from a higher concentration towards the lower concentration, whereas the eddy diffusion, it is also known as the turbulent diffusion. It is the diffusion due to the turbulent motion of the liquid that is present in the system. So as a result of chaotic and irregular motion of the particles, eddy diffusion occurs. Next, steady state and unsteady state operations. So in this lecture we are going to see about the steady state diffusion in a fluid. So in steady state operation, the concentration profile of a species involved does not change throughout the process. So the concentration will remain constant throughout the process, and the steady state condition is given by the dou C by dou T, that is the partial differentiation of concentration with respect to time is 0. Since there is no change in the concentration, the change in the concentration is nil. In unsteady state mass transfer, the concentration of the species involved will change with respect to the time. So the rate of mass transfer varies as the system approaches equilibrium of the steady state. Fick's first law of diffusion states that the flux of the species due to the diffusion of the species is proportional to the negative gradients of its concentration. Here the flux is the how much movement of the molecule is happening from the higher concentration region to the lower concentration region, and diffusion is the process but by that the molecules move from the higher concentration towards the lower concentration. So the measure how much molecule is moved is proportional to the negative concentration gradient. So that is given by Ja is equal to minus dAB dou Ca divided by dou Z. So this law is applied only for the steady state diffusion process where the concentration profile will not change with the time. So here Ja is the molar flux of the species A with respect to the time. So moles per area into time. So that is the unit of the molecular flux, and dAB is the diffusion coefficient of the process. So diffusion coefficient of the diffusivity from A to B, diffusion of molecule A towards the from the end A to end B. Third one is dou Ca divided by dou Z is the concentration gradient. So this dou Ca is the concentration of the species A. So Ca it can be given as Ca is equal to Xa into C. C is the total concentration of the species that is present, and Xa is the mole fraction of A that is present in the mixture. So Ca concentration of A can be given as Ca is equal to Xa into C. So by substituting that we can get this equation, that is Ja is equal to minus C into dAB into dou Xa divided by dou Z. So in a steady state operation, the diffusivity is same for the diffusion of A in B or a B in A. So in that is true in the steady state operation. Consider two gases A and B of equal volume, both are placed in two boxes connected by a tube. So assume there are two boxes and these two boxes are connected by a tube. So that will have a narrow opening. So this consists of gas A and this consists of gas B. So both the containers are maintained in a constant pressure and the net moles of A diffused in one direction. So due to the pressure is maintained in a constant direction, the moles that of A that is diffusing in this direction is equal to that of moles that of B that is diffusing in that direction. So hence the net flux, so the amount since this is approaching the equilibrium, the molecules of A will transfer to the molecules of B and molecules of B will transfer to the A. Since the pressure is maintained at a constant, the amount of A transferred is equal to that of amount of B transferred in this direction. So that will be equal to that of JA is equal to minus JB. So that the amount of molecules transferred, that is the flux. So the flux is equal to that. So how much is moving in this direction is equal to that of how much is moving from that direction. So that is why JA is equal to minus JB. Since the pressure is constant, P is equal to the partial pressure of A and partial pressure of B, and which is also remaining constant. And in a steady state operation, again the concentration is not changing throughout the time. So the total concentration will remain the same. So Ca and Cb, sum of Ca and Cb will be the total concentration, which is also remaining a constant in this process. So by differentiating, Ca is equal to C is equal to Ca plus Cb. So if we differentiate on both sides, this differentiating a constant will give you 0 and dCA plus dCb. So rearranging this, we will get dCA is equal to minus dCb. So writing the fixed law component for the B, that is JB is equal to, by substituting the fixed law for the flux of B, so JB is equal to minus dBA into dou CB divided by dou Z. Substituting the flux in the equation, this flux in the equation 1.2, that is previous equation, J is equal to minus JB. Substituting the flux in this equation gives minus DAB into dou CA divided by dou Z is equal to minus of this is the JB content. So minus of minus dBA. So this minus and this minus will cancel out and become a plus. And we know that dCA is equal to minus dCb. So dCA can be written as minus dCb. So that it will give you a minus here, and this minus and minus will cancel. So this dou CB divided by dou CZ and this dou CB divided by dou Z will cancel out each other, and we will get the DAB divided by DBA is equal to DAB is equal, and we will get DAB is equal to DBA. So this DAB is the diffusivity of A towards B and DBA is the diffusivity of B towards A. So in a steady state condition, we are getting that diffusivity is the same in the diffusion of A in B or B in A. So next, how can we calculate the net molar flux of the diffusion in a steady state fluids? Steady state diffusion, net molar flux is calculated. A general expression for flux, this flux is, Na is the molar flux. So molar flux can be expressed as the sum of molar average velocity and the diffusion flux. So this component Na plus Nb into Xa is the molar average velocity, while this DAB and dou Ca divided by dou Z, that is the molar diffusion flux Ja. So here Na is the flux due to the presence of N is equal to Na plus Nb. So we have divided and written it as like this. So applying equation 1.9, which is present in a different diffusion directions. So Na is equal to Na plus Nb into Ca divided by C. So similarly we have written earlier, that is C is equal to Xa into Ca. So Ca is equal to Xa into we have written previously, that is Ca is equal to Xa into C. Similarly, by for solving for Xa, we can get Ca divided by C in this equation. Substituting this, we will get this equation, and rearranging and integrating, we are rearranging so that all the component of Ca related to Ca will come into one side and all the components related to dz will come into one side. So, by rearranging and integrating this, we will get this equation, equation 1.12 integral Ca1 to Ca2 minus dCa divided by Na into C minus Ca into Na plus Nb is equal to 1 divided by C into dAb integral of Z1 to Z2 into dz. So, the molecule is moved from Z1 to Z2. So, that is what given as the limits of the integral. So, rearranging again after integrating, we will get the equation C dAb divided by Na plus Nb into ln of Ca2 minus C into Na divided by Na plus Nb divided by Ca1 minus C into Na divided by Na plus Nb, that is equal to Z2 minus Z1, which is equal to Z. So, again rearranging this by multiplying Na on both sides, we will get the equation. So, this equation Na is equal to Na divided by Na plus Nb into C dAb divided by Z into ln of Na divided by Na plus Nb minus Ca2 by C divided by Na divided by Na plus Nb minus Ca1 by C is the steady state diffusion equation for a fluids. In this lecture, we have seen what is diffusion, what are the types of diffusion, eddy diffusion and molecular diffusion. We have seen about the steady state and unsteady state operations and Fick's law, how the Fick's law is applied to the steady state operations, and we have seen that diffusivity is same for A to B or B to A, and we have seen the calculated the net flux of the steady state diffusion in fluids. Those are Na is equal to Na divided by Na plus Nb into C dAb divided by Z into ln of Na divided by Na plus Nb minus Ca2 by C divided by Na divided by Na plus Nb minus Ca1 by C. So, this is the equation for the steady state flux in the liquids. Thank you.